So, I want to talk a little bit about the relationship between radians and pi. Very important for rotational kinematics, just trying to relate how something turns or spins like a wheel, and also distance. So you probably remember that pi is 3.14 plus it goes on, but we're only interested in just a few first digits. So what we have here is, let's prove where that comes from. So we have a can, and I've already taken the time to measure the diameter of the can, like so on this tape. And all I'm interested in is the actual diameter itself, not the measurement or units. And all I'm just showing you here is as I walk around, so there's 1, 2, making sure my tape is started on a nice mark that I can remember back, and then I'm going to circle around, and lo and behold, we get 3 times around plus a little change, or in other words, this 0.14, and that is just going to be the ratio between the circumference and our constant pi times the diameter. So we have our circle here, and we've gone around, and we've just compared the diameter to the circumference. So let's do the same thing, except this time let's look at radius. And I've already taken the time and marked off my tape here, so you can see where the radius is of my object. Once again, I'll put it on something that's recognizable for the reference here, right here on the start of this printing of this box. Going around, notice when I'm about halfway around on the other side, all right, it's still 3 plus a little change, and we go all the way around, and we come back, and we notice that we hit here once again where we're measuring our tape, and it's 2 pi r. In other words, it's 2 pi around the can times r. And that's where the concept of radians comes from. And the nice thing about it is it doesn't matter the size of the circle. This ratio, or in other words the circumference again, with 2 pi, is always related to r. So it doesn't matter what the size of the rotating object is. Whether it's a large wheel or a small wheel or a can, all of these objects, the ratio between the two, between the circumference, the distance around, and whether we look at the diameter, we get pi, or whether we look at the radius, we get 2 pi. So for us, what we have here, the r here, is the thing that is carrying all the units. Same thing with the diameter. So it doesn't matter whether we measure it in inches or we measure it in centimeters, or meters, or kilometers for that matter, notice that the units will cancel and we'll still get the ratio of pi. So let's review. What is pi? Pi is the ratio of the circle's circumference to its diameter. The diameter of the circle is the distance from edge to edge, and the circumference is the distance around the circle. If we look at the relationship between pi and degree here, we have half a circle is 180 degrees, or pi, and a quarter of a circle is 90 degrees, or pi over 2. So, if Shaun White does a 1080 degree stunt, how many radians does he turn through? How many rotations is that? Pause the video and try to answer. It's okay, I'll wait.
He literally took that trick that he can do in the pipe and in 3 tries learned how to do that.
How did you do?
And the money booter in Mega
If you
Mode.
answered Shaun White moves through 6 pi, or about 19 radians, you would be correct. The number of spins Shaun White does in the air is 3 rotations.
All those guys have an arsenal of tricks.
Well, we're going to watch Shaun play the learning game.
So we would like to discuss the relationship between linear variables and angular variables. So in 1D, or one dimension, you're probably familiar with x, usually in units of meters, v, meters per second, and acceleration, meters per second squared. These have counterparts in terms of angular variables is theta, which we already have talked about it being expressed in radians. Omega, which can be written as radians per second, and then alpha, radians per second squared. And we can sometimes write these as just rads per second, rads per second squared. And these are all related through r. Now, some ways you've already experienced this. For example, on a circle, a radius r sweeps out an arc length of s. So s is equal to r theta. Theta is the angle through which r turned, giving s. If there's speed involved, in other words, if r is traveling in terms of radians per second, or omega, a point on the rim is going at v. So v is related to r omega. And finally, if that same wheel, radius r, is accelerating, going faster and faster in terms of angular speed, the acceleration at the point on the surface ends up just being A is equal to R alpha.